So, last class first we have discussed the time optimal control, means initial state. If the initial state x of 0 is here, we have to drive the state by proper control action, so that it reach to the origin x t f x t is equal to f, it reach to the origin, but that time requires must be optimal. So, we have discussed the time optimal control by using bang control. Bang control means we are using the combination of plus u max plus 1 comma u min minus 1 combination, or u min minus 1 comma u max plus 1, that combination we will be able to drive the initial state to final state at origin by using the control sequence plus minus combination or minus 1 combination. The time optimal control we have discussed this. Then we have seen the how to really implement in hardware or in a software, how to implement the bang control to drive the initial state to final state in a minimum time. Next we have considered, if you recollect that next we have considered that suppose we have a constraint on the control input and also in the state variables, but we are not dealing with the time optimal control, but minimizing the performance index which involved in minimizing the control effort or control energy, that we want to minimize. So, our statement of the problem is that consider, first let us consider the system A x dot is equal to A x plus B u. Agree? Our problem is to minimize the performance index, which is equal to the what is called your control effort minimization, subject to the constraint that u of t magnitude belongs to u of a, that for all t 0 to t f, so let us call this as t f, and the constant on the state variable is this one. This is the constant in the state variable. We have made it L constants are there, and these constants are differentiable with respect to t, that is the term. So, our problem statement in this case is, given the system which is described in state space model, our problem is to minimize the control effort or the control energy we have to minimize, subject to the condition on input and also constraint on the state. Then this formulation is one of the simplest technique is that you introduce a new variable, that if the number of the states in the system is n, that we have discussed is here, if it is a n, then we introduce one additional variable, let us call n plus 1th state variable. We introduce that this one, that n plus 1 dot is equal to, this is the constraint constraint on the state, the first constraint square multiplied by u s, and u s is nothing but a strictly unit step function. Similarly, second constraint square multiplied by another strictly unit step function, this step function. When this psi of 2 value is greater than 0, then this value is 1. When it is less than equal to 0, that function value is 0. Similarly, the Lth constraint we have written that constraint square into strictly unit step function this. So, this is the new additional state is introduced, this. So, we have made the all inequality constraint now is a equality constraint of that one. What we have already discussed about the U s, that is this U s is the, when it is less than equal to 0, this value is 0, and when it is greater than 0, that it is a strictly unit step function, means 1. Now, look at this expression of 3 and 4. Suppose this may be a situation that psi value some cases may be 0, less than equal to 0, or some cases 0, some cases may be greater than 0. So, whatever this situation is there, this expression is x dot of t, that expression is less than 0 or less than equal to 0, this for all t, this one. The another situation may arise, this situation will arise when all the constants are not satisfied. Then this situation is 0 when all the state constants are satisfied. Under this condition, this will be equal to 0. X n plus 1 dot t is 0 for all times when all the constants are satisfied. So, yesterday only we have come across up to this point. So, we will now continue rest of the part. So, now if we now specify the boundary condition for, if now we specify, if we now specify the boundary condition for equation 3. The equation 3 is that one. Equation 3 is this equation, the new additional state vector, this is equation. Now, you introduce some specific boundary condition for equation 3, that x n plus 1 of t 0 initial time t 0 is equal to 0 and x n plus 1 t f is equal to 0. Because this our things, all the inequality constraint must be satisfied. So, at the terminal condition that must be satisfied, that means this we made an assumption that boundary condition of x from t 0 0 and this is 0. If this is 0 and this is 0, then immediately I can write if x n plus 1 of t 0 is equal to 0 and x n plus 1 t f is equal to 0, then we can write x n plus 1 t is equal to 0 for all t, is equal to 0 for all t belongs to t 0 to t f. How it is? Because if you see the dynamic equation x n plus 1, the dynamic equation, this is equal to 0, because it must satisfy this is equal to 0 when all the constants are satisfied. Now, if you integrate this one, you will get it this equal to what is called 0, provided x t and 0 is 0 and final condition also 0. So, for all the time this will be 0. So, this is x n plus 1 t is the solution of equation 3 if x n plus 1 dot of t is equal to 0 for all t belongs to t 0 to t f. This is the condition for this one. So, now we know that at x n t f also 0, x t 0 is 0. With this assumption, we can make it x n plus 1 t is 0 for all time t if x dot of t is 0. When it will be 0? If all the constants are satisfied from 0 to t f under this condition. So, solution of the problem along with the solution of that problem along with the state equation constraint and additional boundary condition, this is the boundary condition, and with the additional boundary condition we will be able to solve the problem. Which problem? That problem is given the state equation and we have to minimize the performance index, means minimizing the control effort or control energy. subject to the what is called constant on the input as well as constant on the state. That problem we will be able to solve with, if there is a constant on the state, we have to introduce a new additional state variables x n plus 1, and with the knowledge of the constant equation we can write x n plus 1 dot is equal to that expression, x n plus dot is equal to that expression. Okay. And this expression x n dot plus 1, this expression is equal to 0 when all the constants are satisfied over the interval t 0 to t f, this condition. And with this assumption we made it, we specify the boundary, specify the x t n 0 is 0 and x t f is 0. With this condition, boundary condition of this one, this x t n is 0 provided x n plus 1 t is 0 for all time this is equal to 0. When it will be 0? When the inequality constraint is satisfied. So, let us solve a problem of such type of problems. That means, when input there is a constant on the input as well as there is a constant on the state variables. So, example. So, minimize j is equal to 0 to T f half t square of t u t square or d t. Agree? So, you see here clearly this is not the time optimal control. That means, we do not want to drive the state from initial state to final state in a minimum time. Our objective is to minimize the control effort u square t control effort or control energy over the interval 0 to T f, and at T f the state will the original state will drive to the final state at origin. And what should be the sequence of control law for that situation, and subject to what? X 1 dot is equal to x 2. This is the dynamic equation of the system, and x 2 dot is equal to minus 2 x 1 of t plus u of t, and our initial condition is given x of 0, which is nothing but a x 1 of 0 plus x 2 of 0, which is given as a 0 and 1. So, what is our problem? Transfer the initial state to the final state x of T f, x 2 of T f is equal to 0 in minimum control effort with the following constraints. So, this is our problem. What is the constraints are given? This constraint is, first constraint is u of t mod must be equal to less than 1. That mod of u value will be less than 1 for all t 0 to belongs to all t belongs to for all t belongs to 0 to T f. And second condition is state variable constraint, state variable constraint. What is this constraint? X 1 is greater than equal to 0 and minus 1 x 2 is greater than minus 1 less than equal to 2. So, this type of problems we have done in static optimization problem, where we are minimizing the performance index subject to the constraints, agree, and there that equality constraint, inequality constraint, equality and inequality constraint was there. So, we have solved that type of problems earlier, but now this problem is dynamic optimization problem in sorry, not dynamic, that is the yes, dynamic optimization problem. Our problem is to minimize that performance index is nothing but a control effort, minimize control effort. Okay. Subject to the constraint, this is the dynamic equation, and what we have to do, that transform the initial state x, whatever this x of 0, initial state, that is x of 0 to the final state x at origin in minimum control effort with the following state constraints, the following constraints: input constraint and the state constraint. The next question is, let us call this is the equation number 1, this is the equation number 2, and these constraints are equation 3 and this is equation 4. Agree? So, our problem, how to solve this problem? So, we have told you that all inequality constant we have to write in this structure phi psi of this less than equal to 0, psi I is equal to, for our case I is equal to 1, 2, 3. Now, how psi 1 I am writing? So, x 1 is the solution. So, x 1 now solution. So, psi 1, first I am writing psi 1 is what? Psi 1 x of t is nothing but our things is what? We can write this equal to that minus x 1 of t, that is less than equal to 0. So, this problem we have to solve by augmenting one state x n plus 1 state you have to augment. Before that I am writing that inequality constant in the usual form, this form I am writing, psi 1 is x 1. Another condition is that one, if you take the x t in this side, that minus 1 minus this is x 2, minus 1 minus x 2 less than equal to 0. So, psi 2 of x of t is equal to minus x 2 of t minus 1 bracket close is equal to less than equal to 0. This is the second condition, inequality constant in the state. Third, you can write it x 2 you bring it that side is less than equal to 0. So, psi 3 of x t of t is equal to x 2 minus 2 is that equal to less than equal to this, and that is equation number 5, and each constant is differentiable with respect to x of t. So, if you write it better small x, because I have written the small x possibly, yes, I have written small x is equal to x 1 x 2. So, write it small x. So, that all these thing is differentiable with respect to x of t and time. This is the thing. Now, we will form the new additional state. the new additional state. So, we have a second order system x 1 and x 2. So, third state is x 3 dot is equal to, we will write it minus that psi 1 of x of t comma t, this whole square into u of s psi 1 x of t, then minus psi 2 x of t and t whole square u of s psi 2 x of x 1, this is x, so write it x of t or t. This is function of x, means x 1 x 2. This we have seen the inequality constant is a function of x 1 x 2, but in our case some cases is a function of x 1 only, some cases function of x 2, and in some cases may be function of x 1 and x 2 also. That if it is state constant, either it will be a state constant is there, either that the way we are writing here is a function of x 1 or function of x 2 if you in this way. So, you can write more specifically it is a function of x 1, that second one is a function of x 2, and third is psi 3 x of 3 of t whole square u of s psi 3 x of t into comma t. So, you know already what is the value of x, this value. This what is psi 1 of x, just now we have calculated psi 1 of x is minus x 1 t, minus x 1 t. So, psi 1 is minus x 1 t. So, minus x 1 t square, that means x 1 square of t into u s psi 1 x t of t. The next is psi 2 is nothing but a minus x 2 minus 1. So, it will be ultimately square if you take x 2 of t plus 1 whole square u s psi 2 dot function of x or comma t. Then third one is this is x 2 minus 2 value, x 2 minus 2. So, x 2 minus 2 whole square u s psi 3 of 3. Let us call this is the equation number 6. Agree? So, we have written the equality constant values here and square this all these things, and this turns out to be like this way. Now, so equation, you see the equation 6 is 0 when all the constant in 5, that means all the constant in 5 these are true. If all the constant psi 1, psi 2 is true, that means it is less than equal to 0, that means this value will be 0, this value will be 0, this value will be 0. So, equation 6 is 0 when all the state constant, state variable constraints are satisfied. When the state variable constants are satisfied less than 0, that this quantity is less than 0, that means that step function, strictly step function is valid when this x I of t value is greater than 0 or greater than 0, then it is valid. And equation 6 and equation 6 is less than equal to 0 when the constants are not satisfied, when for all t, when for all t the for all t when constraints 5 are not constant 5 are not satisfied. So, this is the we made a conclusion from this one that that equation say x 3 dot is 0 when all the constants will satisfied, x 3 dot is not equal to 0 is less than equal to 0 is not equal to 0 mean less than equal to 0 when this equal to that is this constant are not satisfied. So, now we specify our boundary conditions, specify the boundary condition. What is the boundary conditions? X 3 of 0, our T 0 is 0 and x 3 T f which you do not know is equal to 0. Then immediately you can write it, then x 3 T is equal to 0 since for all t belongs to that T 0 to T f, T 0 to T f, since x 3 dot of t is equal to 0. Why x 3 over 0? Because during this interval if all constants are satisfied then x t is 0. Now, you consider the Hamilton equation, that our Hamilton Hamiltonian equation, including the new state variable, including the new state x 3 of t. So, now what is the Hamiltonian function? Hamiltonian equation or Hamiltonian function, first Hamiltonian function not equation, Hamiltonian function. What is this one? H x 3 of t, this now dimension is x 3 by, that means x 3 is also involved, x 3 of t, then u of t, then lambda 1 Lagrangian multiply, because 3 states are there, 3 multipliers are there, I am writing this one 3 multipliers, and then t. What is this one? See the performing index, our that integral, the part inside the integral is that one. So, you have to write it this one half u square plus lambda 1, lambda 2, lambda 3, which is a function of time. Lambda transpose means lambda 1 is this multiplied by the state equations x dot is equal to a x plus b u, that I am writing state equation. The first state equation x 1 dot is equal to x 2, this I am writing now. You just say that I am writing this equation. this equation x 1 dot, this I can write it x 1 dot, x 2 dot, x 3 dot in terms of a x plus b u form. So, I am writing this multiplied by x 2 of t, the next equation x 2 dot is equal to minus 2 x 1 of t plus u of t plus third equation. If you see the third equation, this is that one I am writing. So, that is, it will lengthy expression, but I am writing, let us call I am writing with a star, and next page I am writing that what is that star. That means 3 1 position, that is the 3 1 position. The space will, I will not get it. So, I will write it that 3 1 position. Then what is this position is that one? Minus, see what I am writing it that one, minus x 1 square minus x 1 square u of s. So, I am writing minus x 1 the psi 1 square dot square, then what is this one? U s psi 1 x is what? Minus x 1 of t. So, this minus psi 2 dot square u s, and that value is, you can write it that psi 2, or you can write it psi 2, psi 2 value is what? Minus x minus x 2 minus 1, that is the psi 2 values. Then this, then third is minus psi 3 square dot u s. What is this psi 3 value? Psi 3 value is x 2 minus 2. So, this is the value of star, that means 3 1 position, that is the value of star, that means 3 1 position, that is the value of the star. So, now you see from this expression what is the Hamiltonian function, that half u square t lambda 1 t multiplied by x 2 lambda 2 t multiplied by minus x 1 t plus u t lambda 3 t multiplied by star, that one. So, I am writing this Hamiltonian function h, which is equal to that x of 3, which one x of t u of t lambda 1 t lambda 2 t lambda 3 t and t, which is equal to I am writing half u square minus lambda 1. Now, see this one, what is the value of lambda 2 into lambda 1 into x 2, lambda 1 into x 2 plus lambda 1 into x 2 plus lambda 2 into, what is the value of that this one lambda 2 sigma psi 2 value is what? Psi 2 value is minus 1, lambda 2 psi 2 value is minus x 2, psi 2 value you just see it here, the very where have you written? Psi 2 value is, you see the psi 2 value. So, minus x 2 minus 1. So, if you take minus common, x 2 plus 1 minus specific with minus, that square. So, it will nothing but a x 2 plus 1 square u s minus x 2 minus 1. plus or minus, you just see, then lambda 3 into that quantity, lambda 3 into this quantity, and lambda 3 is what? Just a minute, just see this one manipulation. So, lambda 1 x 2, I have written lambda 1 x 2, then lambda 2 this, lambda 2, I have written wrong thing here, this should be a lambda 2 minus 2 x 1 t plus u of t. Agree? This is wrong, this is x 2 into u s, not u s, into, there is no u s of t, this one. So, see this one, lambda 1 into x 2, lambda 1 into x 2, I have written this one, then this into this, lambda 2 into minus 2 x 1 plus u 2, lambda 2 minus 2 x 1 plus u 2, this, then lambda 3, next is lambda 3, lambda 3 is lambda 3 into that 3 1 position is that one. So, this is the minus lambda 3 t, and this will be what? Psi 1 square means x 1 square, psi 1 is minus x 1. So, that square is minus x 1 square u s minus x 1 of t, then minus, if you take the minus common from this will be plus, psi 2 is your what? Minus 1 minus x 2, that means, if you take minus common and square, that will be plus. So, this will be a x 2 of t plus 1 whole square u s minus x 2 of t minus 1. This psi 2 value is, say, this one. If you take minus common x 2 plus 1, then square is written, then this. Then next is your psi 3 values. Psi 3 value is what? X 2 minus x 2 minus 2, x 2 minus x 2 minus 2 whole square. See our equation, x 2 minus this square into u s x 2 of t minus 2. So, this is this. This is the Hamiltonian function we have written. Now, let us call that is the equation, number 8. What is the last equation number is? This is 7, 6. This is the equation number 6 we have given. No, this is the page number, and last equation number is 5 and this is 6. And this is the equation number 5, and that is we have given the equation number 6. Let us call this is we give the equation number 7, this all boundary condition equation number 7, and this is the equation number 8. Agree? Now, we can write our necessary condition, the function to be optimized, that means control effort to be minimized. So, what is the our problem is minimize with respect to minimize this with respect to all admissible control vector, or in our case it is scalar, in our case scalar, because single input we have considered that u of t belongs to u of a for all t 0 to t f, for all t belongs to 0 to t f. Agree, that is our constraint. So, minimize all with respect to all admissible control vector this to obtain u star of t in terms of x of t, lambda of t and t. So, let us see what is our necessary condition del h del u of t is equal to 0, and which implies if you see the del h del u, if you differentiate this Hamiltonian function with respect to u, that means u of t is equal to this is term, there is no term u, here is u. So, lambda of t, there is u term is first term and third term, no other terms u is involved. So, this will be a u of t is equal to u of t plus lambda t, u of t plus lambda t, lambda 2 t is equal to 0, and therefore, u of t is equal to minus element 2 of this. Agree? So, let us call this is equation number 9. Since our according to our problem, since u of t mod is less than equal to 1, according to our problem is less than equal to our 1, this weak expression that u of t value will get less than 1 when mod of lambda 2 t is less than 1, when mod of 1 for lambda u of t less than 1 when lambda 2 of t mod will be less than equal to 1. So, then what is our control sequence is there? Suppose if it is less than 1, however, when u of t, when lambda 2 of t mod is greater than 1, the following control minimizes h Hamiltonian function. What is this? Now, look at this. So, this is the condition, necessary condition is there. Since we know the mod of u of t is less than equal to 1, this will be less than equal to 1 when lambda 2 mod is less than equal to 1. But there, what is the guarantee that lambda of 2 always will be less than equal to 1? It may be a situation that lambda 2 of t mod may be greater than 1. In that situation, what should be the control law we should adopt? So, to minimize the what is called the Hamiltonian function. So, our control strategy should be like this way. This equal to minus 1 for lambda 2 of t when is greater than equal to 1. If it is greater than equal to 1, now you see here, if it is greater than equal to 1, now you see I am replacing u is minus 1. So, it is within the limit of that constant on control input. Now, this is plus 1 for lambda 2 is less than minus 1, but it is lambda 2 of 2 for if for or if minus 1 greater than equal to lambda 2 will greater than minus 1 is less than equal to 1. So, this is nothing but a set function. This is we call. So, we will apply the control sequence like this way. If lambda 2 is mod of lambda 2 is less than equal to 1, we will apply whatever the lambda 2 is there, we will apply same thing there. Agree? Now, if it is if greater than 1, we will switch to plus minus 1, because we have to make that u of 2, that if you greater than 1, we have to switch to minus 1, then u of 2 is 1. When u of what is called that u of minus 1, then we will switch to equal to plus 1. Agree? So, this is the controller. So, set function, this is called set function is defined like this way. It is minus 1 when x is greater than 1, x of t again when x of mod of x t is less than equal to 1, when it is a plus minus, this is the plus 1 when it is it is a plus 1 when it is greater than this, and when it is a this minus 1 when x of t is less than minus 1. So, when it is x of t, x of lambda t is greater than 1, this is a plus 1, when this is less than, this is minus 1, and this is when it is a this, then it will be a simply lambda x of t, not this x of t. This is the set function, we can write it. Agree? So, now see this situation, when x is greater than 1, when it is greater than 1, we are putting is plus 1, that means u is minus 1. When it is less than x 2 is less than 1, then we are putting with minus means plus. So, in this way we are making the control sequence of that one. Now, how to solve these problems? Our problem is now to solve. Once again I am telling you this, that this is the necessary condition. This is the necessary condition of this one. Now, you see that this we got it lambda. So, u of t will be minus lambda of t. So, in order to make this thing what is called that the mod of u less than 1, the mod of lambda 2 must be less than equal to 1, then we will get it that 1 mod of this less than equal to this. But when suppose lambda of t is positive, lambda of t is positive, then u is negative, u is coming negative. Suppose lambda of t less than 1, but negative, then u of t is coming positive. So, in this way you have to see. Now, when you will do this one, now let us see this one, lambda 2 is greater than 1. If lambda 2 is greater than 1, then I have to make it lambda 2 if it is greater than 1, then I have to make it with a minus sign. Sorry, I made it this mistakes here, minus sign, because u t is equal to minus of lambda t. When lambda 2 is less than 1 means that minus 2 let us call, agree. So, I have to make it is a positive sign, u of t is positive 1, I have switched to positive 1 only. So, because if it is less than minus 1, then minus minus plus. So, I have to switch to minus 1, because I need not to cross the limit of bound of 1. So, this behaves like a saturation function is like this way: x is greater than 1 is 1, x is less than 1 is this, less than minus 1 is minus 1. This is a saturation function. Anyway, our problem is when x is within the range, when lambda 2 is within the range minus 1 to plus 1, we switch to lambda 2 and this. So, now next what we have to do it? Then we have to solve these problems. So, substituting u star in the Hamiltonian function. If you put the Hamiltonian function x of t u star of t lambda t whose dimension 3 cross 1 t, just I will put is half u star of t square plus lambda 1 of t x 2 of t plus lambda 2, same thing, only u is replaced by u star minus x 1 of t plus u star of t minus lambda 3 of t minus x 1 star of t u s minus x 1 of t plus x 2 t plus, I am just repeating the same expression and writing u star is replaced by u star of t. Agree? Then minus, then is plus x 2 of t minus 2 whole square u s x 2 of t minus 2. This is, let us call equation number, what is the last is 9, we have 8 we have gone 9. Now, this we got it. Now, you find out the state equation, the another further what is the rest of the necessary condition, del h del lambda of t is equal to x dot of t. If you do this one, then you will get x 1 dot is equal to x 2 of t, x 2 dot is equal to minus x 1 of t plus u star of t plus x 3 dot of t is equal to minus x 1 square of t plus u s minus x 1 of t minus x 2 of t plus 1 whole square u of t minus x 2 of t minus 1, then minus x 2 of t minus 2 whole square u of s x 2 of 2, this one. That is what we will get it. This is the state equation, and then you find out co-state vector equation. Co-state vector equation. How will you take co-state vector equation? Then del h del lambda of t is equal to x dot, that is your del x of t is equal to minus lambda dot of t. So, just differentiate Lagrange what is called Hamiltonian function with respect to x of t, and x of t dimension 3 cross 1. Then you will write lambda 1 dot of t expression, that will be finally it will come like this way, lambda 2 plus twice lambda 3 of t and lambda x 1 of t plus u s minus x of t, then lambda 2 dot of t is equal to, you will get it, minus lambda 1 of t minus lambda 3 of t into 2 x 2 of t plus 1 into that bracket is this one into u s x 2 of t minus 2. This is the x 2 of 2 minus 1. This is the minus 1 and here also minus 1. Okay. Then next is your lambda 3 t minus into 2 x 2 of t minus 2 u s x 2 of t minus 2 this. So, this is the expression similar, and then lambda 3 of 3 is equal to 0. So, this is the co-state equation. We got co-state equation, state equation, and we need boundary equation to solve this problem. What are the boundary equations are there? Boundary conditions are x 1 of 0 is 0 given, x 2 of 0 is 1 initial condition is given, then we want to drive the state x 1 at T f is equal to 0, x 2 at T f is equal to 0, then we are not x 3 state at 0 is equal to 0, x 3 T f is equal to 0. This is the boundary condition. In addition to this, there are boundary condition on where you will get another, we will get the that is called for free end point system terminal condition. So, boundary condition for free end point systems. So, that I will write in next class that what is this one, and once you know this co-state equation, you know the what is called the state equation and boundary condition, you can solve this problem. Agree? And depending upon the lambda 2 value, if it is lambda 2 mod of lambda 2 is less than equal to 1, then put the u value is minus lambda 2. If it is greater than 1, the lambda 2 is greater than 1, switch to minus 1, and if it is lambda 2 is less than minus 1, switch to plus 1, and in this way you will drive the state into a origin in a minimum control effort. If you have a both constant in the control input as well as in the state. So, you will complete this one next class. Thank you.